guys, welcome back to another online lesson for Algebra 2. We are continuing on our topic of probability leading into statistics. So today we are going to extend from our introduction to probability that we got in the last target to what we call conditional probability. Conditional probability is basically when we get into situations where we have multiple events and events occur based on what happened before. So let me give you an example. Let's use, let me just talk through an example and I'll write some numbers up here on the screen. So let's say we're looking at a standard deck of 52 cards. Go back to that common example. And let's say our first, we want to look at the probability of drawing a hearts. So if we have 52 cards and we draw hearts, the probability of drawing a hearts on the first try would be 13 out of 52 because there's 13 hearts in the deck of 52. Now let's say the second event is also drawing a heart. Well, if I drew a heart on the first event, now there's one less card in the deck, so now my sample space is 51, and the probability or the numbers in that deck, the number of hearts in that deck would be 12. And this is under the assumption that I'm not putting cards back. So my second event drawing a heart would be 12 over 51 if I do draw a heart on the first event. But let's say I don't draw a heart on the first event. Well, then there's still 13 hearts in the deck, and when I drew a different card, and now there's 51 cards, so the probability of event 2 would then in this case be 13 over 52. So as you can see here, the probability of drawing a heart on the second draw, again assuming I'm not putting cards back, changes based on what happens in the first event. This is what we call dependent events. So a dependent event or dependent events are when the probability of one event relies on a previous event. So in that example, again, the probability of drawing a heart on your second draw relied on whether you got a heart on the first draw or not. So we have a notation for this, and it actually will lead to a formula. So this is notation that we use to talk about dependent events. So basically what this bar, this vertical bar in the middle, means is what we could call the word given. So this is the probability of event 2 given event 1, meaning the probability of event 2 occurs based on event 1 happening. So let's take a look at an example of this. In problem number 1, it says one card is randomly selected from a standard deck of 52 cards. What is the probability it is a jack given that it is a face card? So the probability, the second event here is that we have a jack. Event 2. Event 1 is that it's a face card. So if we took a look at just event 2 on its own, the probability of drawing a jack, if we drew one card and it was from the deck of 52, would be 4 over 52 or 1 over 13. So the probability of event 2 exclusively is just 1 over 13. However, if we have this condition here, given that it is a face card, then the probability of event 2 is now based on event 1. So basically what we're doing is we're reducing the sample space with this event 1. So if we know that we are drawing from just face cards, we know that there are 12 face cards in the entire deck, a king, queen, and jack in each of the 4 suits. So then if we want to draw a jack now, there's 4 jacks out of those 12 face cards. And so the probability in this case actually grows to about 33.33%, or 1 over 3. So because of the condition, the event one condition, it increases our chances here. If we know we're drawing from only face cards instead of the 52 cards in the deck, it increases our chances of drawing the jack. And you can see that in this Venn diagram over here to the right. So everything in the sample space is included in this box. This is every card in the deck. Then event 1 separates just into face cards, and now event 2 selects just the jacks out of those face cards. So everything in event 1 would be now our sample space because it's reduced the sample space. Everything overlapping between event 2 and event 1 would be the number of elements that are going to occur in event 2. So this is one way that probability dependent events can affect probability. Let's go ahead and take a look at another example. Example number 2 says, consider an experiment of drawing two colored balls without replacement. So we're pulling one of the balls out. We're not putting any back in. From a bag containing 5 red, 2 green, and 3 yellow balls. What is the probability the second ball is green if the first ball drawn is green? So again, let's take a look at events. So event 1 is going to be the first ball is green. It's going to be event 1. Event 2 is the second ball is green. So if we want to look at the probability of event 1 occurring just in itself, the probability of event 1 occurring would be there are 2 green balls in the bag, and now out of the total here, there's a total of 10. So event 1 in itself or event 2, they're going to be the same in itself, would be 2 out of 10 chance, or 1 over 5. So drawing a green ball out of the bag of 10 is a 1/5 or 20% chance. But if we are going to draw event 2 based on event 1 occurring, now what we have to think about is, okay, there are 10 total balls. So on the first draw, I take out 1 ball. And now there's 9 total left in the bag. But I also took out a green ball. So the second ball to be green, event 2, there was originally 2 greens. I took 1 out. Now there's only 1. So now I have a 1 in 9 chance of the second ball being green. And so this would be approximately 11.11% chance. So if I was just looking at the probability of drawing out a green ball, it would be a 20% or 1 in 5 chance. But if I look at the probability of drawing a green ball after already drawing a green ball, the second event there is going to be a 1 in 9 chance. Now, let's take an example when we look at um, events that are dependent on one another in a way that we're going to start to include a formula because the counting method that we had here in number 2 starts to get a little bit more complicated. So let's go ahead and take a look at back on the front page a formula that I'm going to extend under this definition here. So the probability that event 2 occurs given event 1 can be found through the counting method, which we did in problem number 1 and problem number 2 because those were easy to count through, but it can also be found through this formula. So remember some notation here. This formula says that in the numerator, the probability of event 2 and event 1 occurs, divided by, in the denominator, the probability that event 1 occurs. So if we take a look at problem number 3, it says, if a 6-sided dice is rolled twice in succession, what is the probability the sum of both rolls is greater than 7, given the first roll is greater than 5? So if we take a look at events here, we can go ahead and let the first roll being 5 be event 1, and the sum of both rolls being greater than 7 be event 2. So there's a variety of ways that we could go ahead and get a sum of greater than 2, or sorry, a sum of greater than 7. We could get a 1 and 6. We could get, sorry, we could get a 2 and 6. We could get a 3 and 6. We could get a 3 and 4, or sorry, 3 and 5, and so on and so forth. So this is just looking at event 2, but if we take into consideration event 1, this is going to allow us to use our probability formula that we just wrote down to come up with the probability that event 2 occurs, given that event 1 occurred first. So I'll just go ahead and write this notation again. So the probability that event 2 occurs given event 1 is the probability that event 2 and event 1 occur over the probability that event 1 occurs. So let's start with the denominator. It's probably a little easier to come up with this probability. What's the probability that the first roll is 5? Well, if I have a 6-sided die, there's only one 5, 6 options. I would have a 1 in 6 chance. But it also says for this probability of the second roll, we're taking into account 2 dice. And so there are 2 rolls, so there's going to be 36 total options here for the probability. So 6 on the first roll, 6 options on the second roll. Multiply those for a total of 36 outcomes. We want the probability that event 2 and event 1 occurs here. So we want the probability that the sum is greater than 7 after rolling a 5. So what would give me a sum of greater than 7 after rolling a 5? I could roll a 5 and a 3. I could roll a 5 and a 4. I could roll a 5 and a 5. And I can roll a 5 and a 6. So I have 6 different numbers I could roll on the first and 6 different numbers I could roll on the second for a total of 36 options. But the probability that I would get a sum greater than 7 after already rolling 5, I have 4 options in that element. And so, in that event, combination of events, so that would be 4 over 36. Then we could reduce this fraction, so 4 over 36. If I multiply by the reciprocal of the denominator, so times 6, this would be, if I reduce the fraction, would be 2/3. So in this instance, we have a 66.67, approximately a 66.67% chance of having a sum of greater than 7 if I already rolled a 5 in the first event. We can also see this taken and broken down and given to us in different methods of information, like tables. So taking a look at example number 4. Example 4 says a survey is taken to gauge public opinion regarding government spending on defense. Part of the results are shown in the table to the right. If one person from the survey were randomly selected, find the probability that the voter felt each of the following. So in problem A, we want to find the probability that spending should increase. And so this is just a singular event. What we can do is we can again find basic probability for this problem, which is the number of elements in the event divided by the number of elements in the sample space. So we look here, 500 total people were surveyed. 200 of those people supported an increase, 300 opposed an increase. So the probability that spending should increase, the total sample space was 500. 200 of those supported the increase. So 200 out of 400, which would be 0.4, or sorry, 200 out of 500, which would be 0.4 or 40%. So problem A is just a basic probability. Now problem B starts to throw us into some conditional probabilities. So it says spending should be increased given the voter age is between 18 and 45 years of age. So if we use our formula here, and you wouldn't necessarily have to use the formula because of the information that's given in the table, but let's go ahead and look at how we could use that formula here. The probability of event 2 and event 1 occurring divided by the probability of event 1 occurring. So the given part is event 2. Their age is between 18 and 45. Spending should increase, or sorry, the given part is event 1, that the age is between 18 and 45 years of age. Spending should increase is event 2. So that can sometimes be confused, but go back to this. Remember, this means event 2 given event 1. And so event 1 is the given part, the voter age. So what's the probability? Let's start with just probability of event 1. It's probably easier to find. So what's the probability that our voters were between the ages of 18 and 45? So if I look at this 18 and 45 category, here's my numbers. 80 were in favor, 270 opposed. So there was a total of 350. So there was 350 voters between 18 and 45 out of the sample space 500. So the denominator of this probability is going to be 350 over 500. The numerator is the probability that both event 2 and event 1 occurs. So again, we're still taking out of 500 total people. What is the probability that voters say that, or the survey responders say that spending should be increased, and they are also 18 and 45 years of age? There was 80 total in that table. So I would have 80 over 500 divided by 350 over 500. And so we could multiply both numerator and denominator to simplify by 500, which would leave me 80 divided by 350, which you could reduce in a fraction. Let's go ahead and just give a decimal percentage here, 22.86%. So 22.86% of voters between the age of 18 and 45 think that spending should be increased. Another way to find this is just using the table here. So you could take the probability and use the statement here to focus on only this portion of the table and realize that it would be 80 out of 350 to give you 22.86%. So you can come to this 80 out of 350 without using the formula in this case because of the information that was given to you. So let's go ahead and use that shortcut in C. Again, this is based purely on the information. So it says, find here, we're going to find the probability that spending should be, or the probability that the voters felt that spending should be increased given the voter is between 46 and 80. So if I use that given, I can focus on just this part of the table. And then take a look at, there was 120 in favor out of 150 total. And so what that's going to give me is 80%. So in this case, based on the information that was provided to you, this would be a quicker way to come up with that total percentage. Now, if you did go the route of using the formula, the probability of event 1 and event 2 over the probability of event 1, the probability of event 1 in this case would be, again, spending should be increased. Sorry. The event 2 would be spending should be increased, and the given event 1 is the voter between 56 and 80. So what I would get is 150 over 500 and 120 over 500 if you use the formula, which would simplify to 120 over 150. So the formula is useful in some cases where you are limited in your information, like in problem number 3. Can be useful in cases like problem number 4, where we are given a little bit more information, but we can also find some shortcuts by using that given to focus on just certain pieces of the information. So like in C, we use the given that the voter is between 56 and 80 to focus on just this table, this line from the table. Now, this concept can be extended a little bit. So we looked in these cases just some examples where we only worked with 2 events. But if we take a look at problem number 5, we're dealing with more than 2 events. We're going to deal with 4 total events. So in problem 5, it says 4 cards are drawn without replacement from a well-shuffled deck of 52 cards. So we're drawing a card, then keeping it, drawing another, and so on and so forth. What is the probability that four aces are drawn? So in this case, let's go ahead and let just D represent an ace is drawn. And I'm going to use D instead of A because you'll see the notation A might have been a little confusing here in a little bit. So in this case, we don't necessarily need to go back to that dependent probability formula. You could, but that would create a little bit more work. We can use counting in this example. So basically what we would have here is the extension of our idea of probability. So on the first draw, we're going to find the probability of drawing an ace on event 1. And so let's call that probability of D sub 1. And we could probably find that pretty quick. There's 4 aces in the deck, and there's 52 cards. So the probability of drawing an ace there on our first draw would be 4 out of 52. Now we can extend this. So now our second event is the probability that we are going to draw an ace on our second draw, given that it already occurred on our first draw. So what we can do here then is um, just use a counting method instead of using the formula. The formula would work, but what we know is if I drew a card already, there's 51 left in the deck. And if I drew one ace already, there's 3 aces left in the deck. And so these are events that we are going to have to multiply together. So 4 over 52 would be the probability of drawing an ace first. 3 out of 51 would be the probability of drawing the ace after already drawing one. So drawing the ace second after already drawing one. And so if we want to find the probabilities of this total occurrence happening, we would need to multiply these separate probabilities together. We can continue this. So the probability of drawing an ace on the third try, given that we already drew it on the first try, and we drew it on the second try. Again, I can use some counting methods here. If I've taken 2 cards out of the deck, there's 50 cards left. If I've taken 2 aces out of the deck, that means there's only 2 aces left. One more time, because we're drawing 4 cards, so now we would be drawing an ace on the fourth try, given that we've already drawn an ace once, and an ace on the second try, and an ace on the third try. So this would be, now I'm left with 49 cards, because I've already drawn 3 out of the deck, and only 1 ace remaining. So multiplying each of these individual probabilities that would give us the probability that this would occur in succession. So we have a 4 out of 52 chance of drawing the ace on the first draw. We have a 3 out of 51 chance of drawing an ace after already drawing an ace. We have a 2 out of 50 chance of drawing an ace after we've already drawn 2 aces, and a 1 out of 49 chance of drawing an ace after already drawing 3 aces. So if we want to put these all together then into one probability that this is going to happen one after another, we would do 4 divided by 52, and you could reduce these if you wanted to, times 3 divided by 51, times 2 divided by 50, times 1 divided by 49. Your calculator is likely to put that into scientific notation. Remember, this e to the negative 6 just means 10 to the negative 6 power. So we would move that decimal place over 6 places. So this would be 0 point with 5 zeros. 1, 2, 3, 4, 5. And then 3, 6, 9. Yeah, sorry, I had to count that and make sure. So if I wanted to put that into a percentage, this would be the fraction down into a decimal. If I wanted to put that into a percentage, this would move the decimal place over 2 more places to the right. So my percentage would be approximately 0.00037. I'll go ahead and round that to 37% chance. So you have, if you're going to draw 4 cards, you have a 0.00037% chance of drawing 4 aces in a row. So this is the idea of conditional probability, dependent events stretching through multiple events and using our counting methods to come up with those probabilities. Now, we also have events that don't rely on each other, and that's most of what we've been working with so far this unit. So an independent event is when a second event does not rely on the first event, or on an event that comes previous to that. So for example, let's say I'm shooting a basketball and I shoot a free throw, make or miss, and then I shoot another free throw. The second event, in reality, there's the mental component, but the second shot does not rely on the first shot going in. It still could or could not potentially go in. Most of the time, we can identify this pretty conceptually by just kind of looking at the scenario and seeing, does the second event rely on the first? But there's also a mathematical way to go ahead and break this down. So let's say if we have any two events, if the probability of event 2 given event 1 is the same as the probability of event 2, then event 1 and event 2 are independent events. So for problem number 6, let's take a look at using the spinner shown here to the right. So if you have the notes packets, it's in there. If not, notice that it's got 8 sections, and each of those sections should be congruent. So in A, it says define event 1 as the first spin is a 3, and the second spin is a 7. Event 2 is the second spin is a 7. Are these two independent? Are these two events independent? So conceptually, we might say yes, these are independent events. But let's go ahead and take a look at this and take a look at it from a mathematical or algebraic perspective. So the probability of event 2 given event 1. Remember, that's the probability of event 2 and event 1 over the probability of event 1. So let's just go with the probability of event 1 first. The first spin is a 3. There is a 3, sorry, not a 3. There is a 1 in 8 chance that the first event, or the first spin, is a 3. So 8 equal sections, we spin it, it could land in the 3 or 7 other places. Now, the probability that event 2 occurs and event 1 occurs would be in our numerator. So if I spin it twice, there's 8 possible options on the first spin, 8 possible options on the second spin, for 64 total combinations. Out of that, if the first spin is a 3 and the second spin is a 7, the only way to go with that is to get 3 and then 7. So there's 1 out of 64 chances to end up with 1 and 2. So if I simplify this, 1 over 64 divided by 1 over 8 would be the same as 1 over 64 times 8, which is 1/8. So the probability of event 1, a probability of event 2 given event 1 is 1/8. Probability of event 2 in itself, what's the probability that we would roll a 7 or spin a 7 just by itself? It would be a 1 in 8 chance. So we can see that the probability of event 2 given event 1 is the same as the probability of event 2. So these two events are independent. So this is the mathematical approach to it. So go ahead and see if you can pause the video at this point, answer question B, but then also support that with some mathematical evidence. Okay, hopefully you got a chance there to get an answer for B, and hopefully you said that no, these events are not independent. So the event 1 is that the first spin is greater than 2. Event 2 is that the sum of these two spins is 5. Are these two events independent? And hopefully, again, we said no. So the mathematical approach to this would be finding the probability of event 2 given event 1. So again, in the denominator, the probability of event 1. What is the probability that the first spin is greater than 2? Well, that means we could land on 3, 4, 5, 6, 7, or 8. So that would give us a 6 out of 8 chance, which is 3/4. What's the probability that event 2 and event 1 occurs so that the first spin is greater than 2, a 3, 4, 5, 6, 7, or 8. And the sum of the two spins is 5. Well, if I roll a spin a 2, I could then spin a 3. That would give me 5. If I spun a 3, I could then spin a 2. That would give me, sorry, the first spin can't be a 2. It's got to be greater than 2. Let's go back a little bit. So the first spin greater than 2, if I spin a 3 and spin a 2, that would give me a sum of 5. If I spin a 4 and then spin a 1, that would give me a sum of 5. If I spin a 5, it's going to go over and everything else will go over. So there are only two ways that I can spin. First, a spin that is greater than 2, and second, a sum of the two spins being 5. So this would be 2 out of, remember there are 8 chances on the first and 8 chances on the second, so 2 out of 64. So if I wanted to reduce that, 1 over 32. So if I simplify here, let me clear up some space. If I simplify here, the probability of event 2 given event 1 is 2 divided by 64. And if I want to multiply by the reciprocal, times 4 divided by 3 is a decimal approximation of 0.0417. I'm going to go ahead and put that into a fraction. If you put it into a decimal, that's okay. It'd be 1 over 24 chance. So the probability of getting event 2 given event 1 is 1 out of 24. The probability of event 2 in itself would be the sum of two spins being 5. Remember, again, there are 64 total options. So the sum of two spins, if I spin it twice, there's 64 total options. Just the sum, not even worrying about what happened in event 1. The sum of two spins being 5, I could get a 1 and a 4. I could get a 2 and a 3. I could get a 3 and a 2. And then I could get a 4 and a 1. So this would be a 4 out of 64 chance, which would, if we reduce, is 1 over 8 chance. So these two are not independent of one another because the probability of event 2 occurring given event 1 is not the same as just the probability of event 2 occurring on its own. So this is a mathematical way to check to see if events are independent or dependent. Again, you could probably, most of you guys can probably go ahead and just read these scenarios and identify that, but we have this option of checking. Let's go ahead and move forward. Just kind of some application problems here, and some different way to look at this information. So problem number 7 says the graduate department at Cahokia University is trying to establish a policy regarding the number of times a student should be allowed to take an entrance exam. Over a period of time, data on pass-fail rates are collected, and the results are shown in the table to the right. Find the probability of a student failing the first attempt and then passing on the second. So what we're looking for here is, again, some dependent events here. So we want the probability of a student failing the first attempt and then passing the second attempt. So what we might say is event 1 is failing the first attempt. And event 2 then would be passing the second. So what I want to find is the probability of both of these things happening. Now, if I take a look at that formula that we've been writing out, the probability of event 2 given event 1, this is equal to the probability of event 2 and event 1 over the probability of event 1. What I'm looking to find here, notice this says find the probability of event 1 and event 2. So what I'm looking to solve for is actually this place in the equation. So I could do a simple rewrite of the equation by multiplying both sides by the denominator. So the probability of event 2 and event 1 occurring is the same as the probability of event 1 given the probability, or sorry, probability of event 1 multiplied by the probability of event 2 given event 1. Now the reason that this is important in this specific problem is this table is already accounting for the dependence of the events. So we have a first attempt pass fail rate. We have a second attempt pass fail rate. We have a third attempt pass fail rate. Great. What this is giving us is numbers of students that passed or failed in the second attempt, given that they already failed on the first attempt. And this would be the number of students that, or the percentage, the rate of passing and failing, given that they already have failed on the first and second attempts. So there would make no sense for a student to pass it and then take it again. That's not going to happen. So this is already taken, this chart right here is taken into account the dependence of events. So what we want to find again is the probability of the student failing the first and then passing the second. So what we can do then is take the probability of event one, which is fails the first attempt, which is 36%. And let's just write that again as a decimal when converting to computational, 0.36. And then we want the probability that event two given event one, so that they pass, given that they failed the first one, that's shown here as 70% or 0.7. So because this formula takes into dependence, the dependent events into account, we can go ahead and rewrite this formula and then figure out that there is a 25.2% chance that a student will fail the first exam and then pass the second exam. So if they're making decisions on where to limit the number of times a student should take the entrance exam, they will realize here that if they limit it to a first attempt, they're going to cut 25% of the students that are qualifying to attend their graduate department. Now let's go ahead and take a look at B. B is going to take this a step further, and it says find the probability of a student failing the first two attempts and passing on the third. So we can basically extend the idea of what we did here in the first problem in problem A. So I'm going to have to write a little small here. So we're going to have to find the probability of the student failing the first two and passing on the third. So event one is going to be failing the first try. Event two, in this case, is going to be failing the second try. And event three is going to be failing the third try, or sorry, not failing the third try, but passing the third try. So what we want to find is the probability of a student failing the first two and passing the third. So the probability of event one failing the first one and event two failing the second one, and event three passing the third. So this is going to be the probability of, I'm going to need a little more space, so I'm going to scoot this over here a little bit. So this is going to be the probability of event one, which is failing it, times the probability of event two given event one. So again, they are only taking the second exam if they've already failed the first, times the probability of event three given event two and event one already happened. So probability that they're going to pass given that they already failed the first and the second times. So what we get here is the probability of event one. So failing the first attempt is 0.36 times the probability of event two given event one. So again, they're only here in the second attempt category if they've already failed the first category. So this would be 0.3. So they're failing the first and the second. Then now we're in the third category. This is finally getting to pass. Would be 0.25. So this would be after they failed first and second, they pass the third. 0.25 of those people that fall into that category would actually pass that exam. So we can figure out the probability of all the students that they admitted passing or failing the first, the second, and then passing the third by multiplying these numbers together. 0.36 times 0.3 times 0.25. Sorry, not plus, times 0.25. And so the probability of this occurring is about 2.7%. So when they're looking at where to limit the number of students or the number of attempts on an entrance exam, you might cut it after the second attempt, because 25% of their students is able, or 25% of the people they admit failed it the first time and then passed the second time. But then only 2.7% of people that they admit failed it the first time, the second time, and then passed on the third attempt. So here we have again an extension of the dependent event formula that we were given, and how this relates to solving for different pieces in that formula. Now, there is one other topic that we want to cover in this conditional probability target, and that is the topic of what we call expected values. Expected values in terms of probability and statistics are one of the most, at this basic level, one of the most useful things that we could explore and learn about. So basically, expected value or mathematical expectation is the expected return on a game of chance, assuming that it is played a large number of times. So for instance, we could take the lottery. What is the expected, let's just use some scratch offs. Let's say, what's the expected return on buying a scratch off every ticket every single day for the entire year? Or you could talk about maybe casino games. What's the expected return on playing the game roulette over and over and over again? So one of the key things here is that this number becomes more accurate with the increased number of trials. So the expected return is again under the assumption that we're playing over and over again. And what we're going to get for this is a formula. So here's a formula. Now this formula is going to take into account what we call value. So EV, this stands for expected value, just capital E, capital V. We know this notation P of E1, this would be the probability of event 1 occurring. V1 would be the value of event 1. So V sub 1 is going to be the value of event 1. And same thing going on. So we would find the probability of event 1, multiply it to the value of event 1, and then add the probability of event 2, multiply that to the value of event 2. And we continue this idea for however many events exist. So let's take a look at an example. An example is in problem number 8 here. We have a group of supervisors that have designed a spinner that's shown here to the right, also in your notes packet if you printed off the notes, to assign work hours to volunteers. If the spinner lands on a circle, the volunteer spins again. If the spinner lands on a target, the volunteer will work 1 hour. If the spinner lands on a frown, the volunteer will double their work time and work for 2 hours. But if it lands on a smile, the volunteer wins 6 hours of help from the supervisors. So kind of a game to assign work hours. On part A, it says, from the prospective volunteer's point of view, what is the expected value of the spinner? So we can use this equation. The expected value is equal to the probability of an event occurring times the value of that event, and then adding in every event. So if I'm trying to find the expected value here in 8A, the first event I could get is that the spinner lands on a circle. So there's 2 circles on the board, and we're going to assume that these again are all in even pieces. And so there are 2 out of 8, or a 1/4 chance that the spinner lands on a circle. We're going to multiply that probability times the value of that event. So if it lands on a circle, nothing happens. The volunteer spins again. So this would be 1/4 times 0. So the first event, landing on a circle, doesn't really have any contribution. The second event is that it lands on a target. So we can see there's 2 targets on this spinner, so a 2 out of 8 probability, or a 1/4 probability that it lands on a target. The volunteer will work 1 hour. So if we're from the volunteer's perspective, ideally we would like to have help come our way from the supervisor. So we're going to call this value -1. So if it lands on a target, we're essentially giving away an hour of work. If it lands on a frown, so we can see here there's 3 frowns, so we have a 3 of 8 chance landing on a frown. The volunteer will work double time, so we're going to give 2 hours of our time away. So the value here would be -2. Finally, the last option is that it lands on a smile, and we can see 1 smile on the board, so 1 out of 8 chance. There's a 1 out of 8 chance that we would get, in this case, 6 hours of help from the supervisors. So that we would call that a +6 because we are gaining work from other people. So as we simplify this, the expected value then, let me simplify these fractions down a little bit. 1 times 0 is just 0. -1/4 plus 3 over 8 times -2 would be -6/8. So let's make this minus 3/4. And then plus 6/8. So plus 3/4. And you could always do this in your calculator, but then the -3/4, the +3/4 cancel out. So the expected value is -1/4. So essentially what this means, the expected value is -1/4. Remember, negative is we are giving something away. So for every spin, if we spin over and over again, for every spin, we can expect to give 1/4 or a quarter or 15 minutes of work. So every time we spin on, if this is done over and over and over and over again, based on the probabilities of landing on these different parts, the expected value is -1/4. So for every spin, we will give -1/4 hour, or -1/4 means we're giving. So we're going to give 1/4 of an hour of work, which would be 15 minutes. So if we spin 10 times, we could expect to give 150 minutes of work to our organization, or whoever created this spinner. Part B says, what value would be assigned to the smiley face if the supervisors wanted the spinner to be fair? So one thing to note about expected value, and I didn't put it down there when we came through here, but let's add this in now. If EV is equal to 0, the test or game of chance is considered fair, meaning that it doesn't favor one side or another. So if we want this spinner board to be fair, we can't change the board. We've already cut it into sections. I mean, we could change the board. We can turn a frown into a smiley face, but that would change the number of ways we could land on things, not necessarily the expected value. So if we want the expected value to be fair, what we could do is we could adjust what we add to the smiley face, or what the smiley face is worth. So what I'm going to do here is I'm going to keep the same equation, essentially, but instead of solving for EV, the expected value, we want the expected value to be 0. So we're still going to have a 1/4 probability of hitting a circle, which has no effect. A 1/4 probability of hitting a target, which means we give away an hour of work. A 3/8 probability of hitting a frown, which means we give away 2 hours of work. And then finally, a 1/8 probability of hitting a smiley face. But we're going to change what the smiley face is worth so that this is fair. So let's make that a variable. We could just make it x. So if I simplify this, this would be 0 equals -1/4 and -3/4 plus 1/8 x. If I simplify again, 0 equals -1 plus 1/8 x. Now I can solve for x, so add 1 to both sides. then multiply by 8 to both sides. So x equals 8. So for this to be fair, the smiley face could be worth 8 hours of help. So this way, over a group of, or over, if we assign the smiley face to be 8 hours worth of help over a large number of spins, those hours would balance out. So you might end up giving 15 hours of your time to your volunteer organization, but you could expect about 15 hours of time back from these supervisors to help you. So this is what expected values does, is it gives us a number, it assigns a number to interpret what we can expect or what we can assume to get benefit from a game of chance, if you will. Let's take a look at another example. Problem number 9, a claw machine game. So you've probably seen these at stores. Um, they were more common when I was growing up than when you guys, but you've probably seen them around where you have the glass case and there's items in that glass case, and you work a little joystick, you drop the claw, you try to get an item out. So it says the claw machine game allows players to move a claw until it is directly above a desired prize located within a case. The player drops the claw in hopes it will latch onto the prize, lift it, and drop it into a chute that delivers the prize to the player. For the claw machine, the game delivers a $6 prize 2.5% of the time, $3 prize 5% of the time, and a $1.50 bag of candy 20% of the time. It says if it costs $1 to play the game, what is the expected value for the player? So from the player's perspective, this is actually what they basic form of what they use to figure out how much to make a player pay. So let's say expected value is what we're looking for. The cost is $1 to play the game. So we put $1 in and we never get that dollar back. So the first option is that a $6 prize comes out. That's 2.5% chance. So I'm going to go ahead and put that into a decimal. So that would be 0.025 as a decimal. So the probability of getting a $6 prize. Remember, if you get the $6 prize, essentially you paid $1 to that. So the value of that prize is basically $5 because you did give $1 that you don't get in return. Now, the second event is that we get a $3 prize, and that happens 5% of the time. So converting that percentage to a decimal, 0.05, it's a $3 prize, excuse me, a $3 prize. Again, you put $1 in there, so really you come out $2 ahead, a positive $2. Then 20% of the time, or zero point 0.2, you get a $1.50 bag of candy. So you come out essentially 50 cents or 0.5 ahead. Now, this is the percentage of getting these prizes, but this isn't the only thing that could happen. You might get nothing. So you might miss, or the call might often does drop the prize as it comes across um, the apparatus. So the percentage of winning is the 5% plus the 2.5% plus the 20%. So you have a 27.5% chance of winning, which means you also have a 72.5% chance of losing. So we have to take into account that event. You get nothing. So 0.725 is 72.5% that you get nothing. And we would multiply this by -1. The reason we would multiply this by -1 is because you put that dollar in, it does not come back out, so you lose that dollar. So you have a 72.5% chance of losing your dollar. So all in all, if we combine all of these together, we can get an expected value for the machine. So 0.025 times 5 plus 0.05 times 2 plus 0.2 times 0.5 plus 0.725 times -1. So I'll just go ahead and subtract 0.725. And this gives me an expected value of negative 0.4. So what this means is that for every dollar that we spend in here, over time, we can expect to lose 40 cents. So on basically on average across a large number of opportunity or a large number of times of playing, we can expect to lose 40 cents every time we play the game. And that's from our perspective. Now, if it's from the perspective of the machine maker, they see this as gaining 40 cents every time they play. So their expected value would be a little bit different. So let's go ahead and take a look at that case. B, if a vendor wanted an expected value of a 60-cent profit, what should a patron be charged to play the game? So now I'm going to take a look at this from the vendor's perspective. So from the vendor's perspective, we want a profit or an expected value. So the EV portion is going to be zero point 0.6. So the 0.25% or 2.5% chance of getting a $6 prize from the vendor's perspective is I'm actually losing $5 here. They put a dollar in there, but I'm giving away a $6 prize. So from the vendor's perspective, I'm losing $5. This would be a negative 5. So perspective is important here. From the 5% chance of winning a prize, or 0.05, if they win that $3 prize, I get a dollar, but then I give away a $3 prize, so I'm losing $2 as a vendor. Then finally, for the bag of candy, that happens 20% of the time, I'm losing 50 cents. Now, when the player gets nothing from as the vendor, I'm winning. So 0.725. Now, I'm going to determine what to charge the player. In the previous problem, we knew that it cost a dollar to play the game, but maybe we noticed here, that would only give me a 40-cent profit every time they play. I want to up that. So I want that to be a 60-cent profit. I'm going to make this X, and I'm going to figure out what I need to charge the player. So if we simplify this, the expected value for me, now that I'm the vendor, is plus 0.0, or sorry, 0.6. Again, these first terms were, three terms were negative here because when the player wins, I as the vendor lose. So I'm going to go ahead and simplify these. So 0.025 times negative 5 plus 0.05 times a negative 2 and plus 0.2 times a negative 0.5. If I simplify all of these, I get a negative 0.325 plus 0.725x. Now I can solve for x, so add 0.325 to both sides. So this is 0.925 plus 0.7, or sorry, equals 0.725x. And finally, I can divide by 0.725x. And now I can come up with the value that I should charge. And so if I take 0.925 divided by 0.725, I would get approximately $1.28 here. So what should a patron be charged to play the game? If I want that expected value of a 0.06 or a 60-cent profit every time they play, about $1.28. Now, if we take this into the concept, we'd probably round that either down to $1.25 or round that up to $1.50. That's common that you only see use of dollars and quarters in these machines, but that $1.28 charge on average would give me an expected value of increasing 60 cents every time a player plays the game. Let's go ahead and take a look at another example. This example is about the game roulette that is played in casinos. So the game of roulette is typically played on a wheel with 38 slots, numbered 0, 0, 0, sorry, 00, 0, and 1 through 36. So here you can see an example of a roulette wheel. You can see those numbers there. The numbers are not in sequence. The 00 and 0 slots are commonly green, and all other slots alternate in color, black, red, black, and so on, enabling players to place wagers in a variety of different ways. The wheel is spun, and then a ball is dropped onto the wheel, and it is equally likely to end up in any one of those 38 slots. To make a single number wager, and there's multiple ways you can make wagers, but to make a single number wager, a bet is placed for any slot except for 0 and 00. If the ball ends up in that slot, the player wins $35 for every $1 they wage. So if I put a dollar on number 29 and the ball ends there, I win $35. If I put $10 on number 25 and the ball ends there, I win $350. So in problem 10, it says Max decides to play roulette for the rest of the evening and repeatedly sorry, I'll have to fix that, and repeatedly places a $1 wage on number 22. Find the probability the ball will land on 22. So this goes back to basic probability here. There are 38 total slots on the wheel. The probability that we would land on 32 is, or sorry, 22 is 1 out of 38 chance. Find the probability that the ball does not land on 22. So the probability, let's let the event be E. So probability of not being E would be 1 minus 1 over 38, which would be a 37 over 38% chance or probability. So the probability that it does land on 22 is 2.63%. Probability that it does not land on 22 is 97.37%. So you might look at this and say, oh, it's not a pretty likely chance that it's going to end up on that number. So maybe I shouldn't pay. But then you might also look or play. But then you might also look and say that, okay, it may be a low percent chance, but I do get a 35 times payout for whatever I put down. So if I play over and over and over again, maybe this is going to pay off because 1 out of the 38, 2.63% of the time, I'm going to win $35. So what we need to take into account here is the expected value of the game to see if it's worth our time to try to become profitable here. So the expected value equation, again, is to find the probability of an event and then the value of that event and add those together. So the expected value for this game, the first event was the ball lands on 22. So the probability of that is a 1 out of 38 chance. The expected value, if we do win here, is $35. So notice this is a little bit different than the claw machine problem. In the claw machine, you paid the dollar and it never came back. In this game, you pay the dollar, but then you win 35, so they give you your dollar back there. So 1 out of 38 chance of winning $35. Now I'm going to add the probability of losing. So there's a 37 out of 38 chance that we lose. And in this case, we just lose a dollar. So the payout for winning is much higher than the loss if you do lose. So what we can do here then is compute these two probabilities multiplied to their values. So 1 over 38 times 35, and then I'm going to subtract 37 over 38 because that's 37 over 38 minus or times -1. And we can come up with this expected value. So the expected value here, if we're going to go in dollars and cents, the expected value is about 0.053, or if you went 0.05, that would be okay. So what this tells us is that if Max here is staying there for a large number of time and just betting on number 22 and betting on number 22 and betting on number 22, he can expect to lose about a little over 5 cents, about 5.3 cents every time for every dollar that he puts down. So maybe it's worth it. He takes a chance and he gets lucky, but this expected value says that over the course of time, you're probably going to lose a little bit of money. Not a lot, but a little. And this is the conclusion of PS.2 notes, conditional probability. So at this point, you guys do have everything that you need to go ahead and get started on the homework. That homework assignment is up, or very soon will be up on Google Classroom. So make sure that you guys are working on that. Monday is Memorial Day, so technically Monday is not a day that I'm expecting you to work. So 4th class days until our next Zoom meeting. Our next Zoom meeting will be on Wednesday, May 27th. So keep an eye out for those details. We will also have our online assessment that afternoon as well. If you guys run into any questions between now and then, go ahead and shoot me an email and we will work it out. Thank you guys for tuning in and have a great day.